Okay, welcome to the last session of POPL Semantics 2. Okay, so for our first talk, Andy Pitts will be telling us about locally nameless sets.
Well, thank you for all still being here. The thing about giving a talk towards the end of the conference is you get to hear lots of other people's talks first. And I realized watching all those talks that my talk didn't have any pictures, no gratuitous pictures in it. So I thought I'd add a gratuitous picture, at least at the beginning. But I think we've got to pass over that rapidly. So what I'm going to tell you about, the context of it, is the enterprise of using interactive theorem provers to prove properties of whole programming languages rather than of particular programs. In other words, proving meta-theoretic properties of languages. And I'm going to revisit a pretty well-trodden area, which is to do with what's the best way of representing languages that involve name-binding constructs in a way that's where it's sufficiently abstract that the representation is oblivious to renaming the bound variables up to alpha equivalence. And the locally nameless method is a rather nice way of doing that that's been around for a few years. But in this talk, I want to tell you something new about it that I discovered recently and draw some possible consequences of this new view of it. So let me begin by reviewing or telling you what the locally nameless representation is. So as the name suggests, it's a combination of sort of named and nameless representations. I'll use a running example from the simply type lambda calculus of a very straightforward kind. So if we look at this term here, so the function that takes something of type B and returns a pair xy. So in the usual sort of named representation, you have some fixed countably infinite collection of names that you use to name variables, and both bound variables and free variables are named. So this y here is a bound variable bound here, and this x is free. Of course, that abstract syntax tree is not very good because it might be that you were typing that term in a context for some reason where, yes, x is of type A, so the term has the function type from B to the product of A with B. But you might also, in the context, have a free variable y, and that's sort of clashing with the use of y as a bound variable. But up to alpha equivalence, we can change the name of the bound variable to avoid that unfortunate collision. And of course, the representation in the name form is not really the abstract syntax tree, but the alpha equivalence class of syntax trees. So it's not a purely inductive collections of things, it's a quotient inductive thing. And if you're using a theorem prover where the main means of construction is inductive definition, so like Agda or Koch, for example, then that's not so convenient. If the support for quotients is not that great, then it's not so good. But the good thing about the representation is at least it's invariant under weakening. So if I weaken my context, let's say by throwing in an extra assumption, I don't have to change the alpha equivalence class for that still to be a valid typing assertion. So that's a nice aspect of the named approach. Well, of course, I mean, as I'm sure you know, you can get back to purely inductive definitions by having canonical representations of equivalence classes, for example, using nameless terms with De Broglie indices. So that's now we've got the natural numbers acting as indices, and I'll use the sort of count from the occurrence out to where the occurrence is bound form of index. So our term now looks like looks like this. Okay, so the bound variable has become index 0 because it's 0 places away from where it's bound. And here this free variable is replaced by this number 2, which is a dangling De Broglie index, right? So it's referring to a binding 3 places out, but there's only one binder in this term, so that's sort of free. Well, we've got back to now something which is purely inductive as a representation. So we're hitting alpha equivalence classes exactly on the nose like this. But the bad thing is that we've lost weakening. So I mean, if for example, so that's a valid typing in the nameless form. And if I weaken the context, say by throwing in this extra assumption, I've got to add 1 to 2 to get 3 to make sure that I have this pointing not to that occurrence of A, which is 2 out, but this one, which is 3 out now. So I mean, obviously, with this very simple example, it's kind of trivial. The shifting that you have to do here is no problem. But in a very large development, dealing with explicit weakening and reasoning about it and its properties is quite irksome. And, you know, I know people have been stopped in their tracks in trying to prove something because of the weight of having to do that. So locally nameless combines these two things together and somehow gets the best of both worlds. So you use indices for the bound variables still, but you use named free variables. So our term now looks like this. We've got the bound variable represented by this De Broglie index. It's 0 pointing at this binder, but the free variable is now called x. Okay. Well, we still have a representation of terms up to alpha equivalence, which is purely inductive, right? Because we're using De Broglie on the bound things. But also at the same time, it is weakening invariant. I mean, so I don't have to change the term. When I weaken the context, it's still going to be a valid thing because I'm using explicit named free variables. So these guys had a paper in POPL in 2008, engineering meta theory, and Arthur Schurgerer followed that up with a journal paper a few years later, and that sets out the locally nameless approach. I mean, it's you know, it was around before that, but these works really popularized it as a useful technique for doing mechanized meta theory. And part of what they point out is that you have to kind of develop a certain amount of infrastructure every time you do a development in the locally nameless style. And I just want to pick out some of the infrastructure that's going to be important to us. Okay, so one operation on locally nameless terms on this kind of representation that you need is so-called opening. So that's where you take an index and replace it by a variable. So I'll use this notation for opening the term by replacing index I by the variable x. And dually, we've got a closing operation where you replace variable x with index I. So these operations come up all over the place when manipulating locally nameless terms. And we have some relations that we also always will need to have around. One is non-occurrence of variables, or freshness, as one might say, and I'll notate it like this. So this says is that x is not a variable occurring in the locally nameless term t. And we also have for indices a non-occurrence form. So locally closed up to some index I means that all the indices that appear in the term are strictly less than I. And actually, the I equals 0 case of this is very important. So that's where there are no indices at all in T, and one talks of the term being locally closed. Not maybe a great term, but that's what's the terminology that's used. So a locally closed term is one that has no indices. So if we restrict attention, if we can restrict attention to locally closed nameless terms, then things are exceedingly nice. I mean, for example, if you did a definition of capture avoiding substitution, you can have a very simple clause for what happens when you substitute under a binder, just structurally pushing it through the binder without changing it. As long as the thing you're substituting is locally closed, then you won't need to do any index shifting when you go under the binder, and this will be a valid thing. So one wants to restrict reasoning so that you're always dealing with locally closed terms. So when you deconstruct a binding form to get at the body, right, you can't just return T because that won't be locally closed. It'll have index 0 in it. So you need to open that index by replacing it with some suitably fresh variable x when you open up the bound form. Well, what fresh x is? Well, there'll always in any context be finitely many x's which are not good, are stale, as it were, and all the other infinitely many ones will be good, will be sufficiently fresh. So you're very naturally drawn to quantify over all but finitely many things, I'll use this notation. So I'll write this and say some property holds for all but finitely many variables. So I mean, for example, the typing rule for typing a lambda abstraction, you could formulate it this way, and it's a nice way of doing it. You can deduce a typing of a lambda abstraction if, for all but finitely many x, it's the case that the opened term with x in it has type B in the extended context where it has type A. So cofinite quantification, I guess it's probably McKenna and Pollock who noted first in this context its importance. I mean, Jamie Gabay and I kind of independently discovered it in the context of developing nominal set theory, and the nominal freshness quantifier is a very special case of cofinite quantification. Here I'll reuse the nominal freshness symbol, this is it backwards or upside down n? I can never remember, to indicate cofinite quantification. But one of the main points of this work, the engineering meta theory and the locally nameless representation paper, is to point out that by using cofinite quantification judiciously, you get a really quite nice and smooth ability to develop meta theory using the locally nameless presentation. Okay, so that's what it is, right? Now I want to tell you something new about it. So up to now, if you were going to do a locally nameless development, you'd have your object level language, the programming language you want to prove things about, and you'd develop your I mean, unless you had some tool support, and I'll mention some of that a bit later, you develop the infrastructure case by case according to what your language is. So the opening and closing operations obviously be defined by recursion over the structure of the terms, and the freshness and local closedness relations would be by induction, structural induction over the terms. So the cool thing is, and it came as actually quite a surprise to me, and expect this to be true, is that actually you can give an equational axiomatization of opening and closing. So there are some equational properties that opening and closing operations always have in the concrete setting of locally nameless syntax. And if you take those as axioms, then actually you can define, using the operations and using the cofinite quantifier, you can define the freshness and local closedness relations and develop a lot of the infrastructure of the locally nameless approach. In particular, developing a notion of finite support, which is itself expressed in terms of opening and closing and cofinite quantification. So that brings me to the main definition in the paper, which is a locally nameless set. So let's fix some countably infinite set of things which are atomic names, disjoint from the natural numbers, which we'll use as De Broglie indices. So the notion of locally nameless set is relative to those choices of particular sets of names and indices. But then an abstract set is locally nameless if it comes along with two functions of this type to give you opening and closing operations for a given index and a given name, satisfying some equations, which I'll show you in a second, and crucially with the property then that every element of the set is finitely supported. And what does finite support mean? Well, it means that for all but finitely many names, the name is fresh with respect to the element S, and there is some index so that S is locally closed up to index I. But the thing is that the freshness relation and the local closedness relation, they're just expressible in terms of the opening and closing operation. So freshness is expressed in terms of invariance under closing, and local closedness here is expressed in this way with invariance under opening. And making the definitions this way and using the equational axioms, you can develop the expected properties. I don't have time in this talk to really kind of discuss the axioms in detail. There are 9 of them. Actually, really, there are only 5 because there's a duality between opening and closing. So that there are 4 pairs of dual equations, and there's one equation which is self-dual. So there are really only 5 things. And I consciously made this part of the slide quite small, so if you're at the back, you can't even read the equations. You just want to sort of get an impression that there are some equations, right? Many of them are kind of properties that if I asked you to write, if you knew this representation locally nameless, and I said, write down some properties of opening and closing, you would write down probably the first 7 out of the 9. I think you probably wouldn't think of the last 2, which came to me in the development rather late on. They're a bit more complicated looking and difficult to remember. They're there for a very good reason, which is that modulo these equations, then you can actually define all sorts of other ways of renaming. So as well as mapping variables to indices or indices to variables, you can rename variables to variables. So you just choose some index which is for which A is locally closed, and there is such a thing because of the finite support property, and get renaming by closing X to I and then opening I to Y, and that definition is provably independent of which I you choose because of actually the last axiom here. And similarly, you can define a renaming of indices to indices. But more than that, you can actually define bijective mappings as well. So you can swap 2 names, for example. What would you do? You just choose 2 indices which are distinct, for which A is locally closed, and close X and Y to I and J, and then open them up in the reverse order, and that will turn out to give us the ability to swap 2 names. And you can swap 2 indices, and you can swap an index with a name. So in fact, you get, once you've got a locally nameless set, the action of any finite mapping of names or indices to names or indices on elements of the set. And because everything's finitely supported, actually you get an action of arbitrary functions, because an arbitrary function will only affect finitely many things because of the finite support property. So these definitions have the expected properties in the sense that, so Andre Pescu has a notion of finitely supported renaming set, which is a similar sort of axiomatization, and this definition here satisfies his axioms, and everything like that is a nominal set in the sense of myself and Jamie Gebel. But never mind about that. The point is that you get the action of any function, and then one is able to state a theorem which kind of pins down why the axioms are, as it were, sound and complete in a certain sense. So if you'll indulge me, I here need a little bit of category theory. I know there are mixed feelings about category theory in this community, but here we go. It's not too bad. Organize locally nameless sets into a category. How would you do that? Well, you just take the morphisms to be functions that preserve the opening and closing operation. So it's just an algebraic sort of thing, right? So that gives us a category of locally nameless sets. So it turns out that category is actually isomorphic to a known category, actually not just a category, but a topos. That's a very nice category which has sufficient structure to model intuitionistic higher order logic and extensional dependent type theory. Let me just explain what this is. So T omega here, that's just the monoid of all possible functions from numbers to numbers. Okay. So that's the full transformation semigroup, as semigroup theorists would say, on the countably infinite set omega. Okay. And we look at then set to the T omega. That's just the pre-sheaf category, which is the sets equipped with an action of that monoid, a left action of that monoid. So that's an example of a pre-sheaf category. And then if we cut down to the full subcategory of objects which are T omega sets, where every element in the set is finitely supported. And there's a standard definition of finite support for actions of function monoids on sets. So that's not that's an existing thing. So that's what this right-hand side is, and it's a pre-existing thing that's already known, and we know some of its properties, and so it turns out to be isomorphic to this. The proof of that is it's quite hard work, actually. There's several ingredients to it, so it's not entirely straightforward, but at the heart of it, there's an existing fact in semigroup theory that gets used. So there's a known presentation of finite full transformation semigroups. So if you take the monoid of all possible functions, not on omega, but on a finite set n, then there are existing presentations of that monoid going back to 1974. And you can relate that to the axioms for locally nameless sets and use that to prove this theorem. But I won't say anything more about how you prove the theorem. What I do want to say is that as a corollary of the proof, one sees that various other categories that people have used to model variable to variable renaming in the context of sort of meta theory of languages. So Sam Staton in his thesis in 2007 had a particular category, and then Jamie Gabay and the late lamented Martin Hoffman had one in 2008, which was actually equivalent to his. And Andrei Popescu, in his IGCAR paper last summer, has yet another category of renaming set, so-called. So it turns out all those categories are equivalent to each other, and they're all equivalent to the category of locally nameless sets. So that's really quite a nice unification of the landscape. We've all been talking about basically the same thing, though the different ways of approaching it look actually somewhat different to each other. So it's in a way, a surprising result. However, that's by the by in a sense. What is this good for, right? I mean, obviously, if your locally nameless set is the locally nameless terms for some specific finitary syntax, okay, and you define opening and closing by recursion on the structure of terms, and you define freshness and local closedness inductively in the usual way, you do get a locally nameless set. So what do we gain by having this more abstract algebraic view of things, right? I mean, one could ask. I hear you asking, as it were. So I'll spend the rest of the talk just sketching. I don't think there's much rest of the talk. Oh. How much time back? None. Oh, damn. When I practiced this, it was much quicker. Oh, well, okay. Let me go to the conclusions then. Okay. So we have an algebra of opening and closing operations. So cofinite quantification plays a key role. Okay. So what I didn't show you is that you can lift binding to a functor on locally nameless sets and use that not necessarily in syntactic situations, but in other ones. So you get sort of locally nameless semantics as well as syntax. And there's potential, I think, for doing some automation in a sort of type class style for getting rid of boilerplate. But I've run out of time, so I'll shut up. Thank you. Yeah.
Okay, thank you, Andy. I think maybe we can take one question while the next speaker sets up.
I guess I just want to ask for a comparison with like working in logical frameworks, because
just speak closer to it.
A comparison with working in a logical framework, because we could do all the meta theory of ML and never once ever think about any of these issues. Because, well, to be honest about it, I would say we think about it precisely once when defining the logical framework, but otherwise never again. And for all the languages you're studying, you just formulate them that way and you're good.
Yeah, but I think a better comparison would not be with the logical framework, but would be with contextual modal type theory, because you do need to be able to reason about things in the logical framework So having that contextual modal logic is one way of doing it. It's just that I think this kind of approach is just a lot simpler. So they're rival techniques, right? I mean, obviously higher order abstract syntax is one way of doing representations. It's not the locally nameless way. And I think there are pros and cons of both ways of doing things, right? Yeah.
The next speaker come
Yeah.